Hey everyone, so welcome to this new tutorial, and today we are talking about parallel transport because I'm going to use this tutorial as a base for future tutorial for more complicated kind of effect or things we want to do, right? So this is a good base to have and point to in future videos. So let's get right to it. What is parallel transport? So parallel transport is a technique that allows you to generate a stable frame, a stable orientation, 3D coordinate system along a curve, right? So, because if you think of it, if you have a curve, you can easily find the position on a curve, but what's the orientation? Like, if you need to place a cube on that curve, what would be the position, like, so the orientation of this cube, right? So basically, that's what parallel transport helps you solve. For example, in game can be used to drive something along a curve, like I know a missile being driven along a curve, a boat, right, with giving bank or not. So here we have a simple example. That's the tutorial, what we're gonna create in this tutorial. And so you can see these are the frames generated, right? So basically this is our up vector, this is our x vector, and the red one is our aim, right? So you see we have the exact same kind of orientation we have in our gizmo here, but it's following the curve. We see if it's going along the curve, and if I grab a point and move it, you can see that the orientation updates, right? So even if I move it like this, the whole orientation updates correctly. And once you do that, there are several things you can do on top of it. You can start to manipulate this space. For example, we see if I can, you can start twisting the space, right? So there are several things you can do. So that's what we're gonna cover today, and let's get right into it. The way I approached it in this tutorial is by having a custom component called parallel transport with few parameters on it, mostly an array of game objects, right? And we use the position to define the position of the curve. That's just only one way you can do it. It's easier to do this way for me. You can define the curve as a mathematical function, a NURBS curve, a Bezier curve. It's up to you. It will work exactly the same. I did it this way because it's simpler and easier to explain. So once you have this array of objects, you just plug them in one by one, and as you saw, you can move them and the script will update accordingly. Then there is an initial vector to provide, and we're going to see that later, and then there is a debug vector scale that I use. That's just to basically how long the vectors are. But in this first part of the tutorial, we're just gonna cover the theory, right? In the second part, we're gonna dive right into the code in Unity and see how it works and how to implement it. All right, so let's jump back into OneNote. So I'm going to try to use the pen so my drawing is not as horrible as usual. It's still gonna be pretty horrible, but if you follow my channel for a while, you know that. All right, so let's get started. What do we need to define a frame, right? An orientation, like a coordinate system, right? So we both want this coordinate system be positioned somewhere, so we need a position, right? And then mostly we need an orientation. If the depends, an orientation, right? So a rotation. So we can express the position super simply with three values, right? X, Y, Z. But how do you express the rotation? So we are going to express the rotation with three orthonormal vectors, right? Which define the X, the Y, and the Z axis. What do I mean by orthonormal? So orthonormal is a composition of two words, normal and orthogonal. So orthogonal means that all the vectors are perpendicular to each other. All the angles you see in this image, although my drawing doesn't give me justice, they are 90 degrees. So for example, you don't have something like this. This is not an orthonormal frame, okay? So you see there is some skewing on the resulting space, and we don't want that. And normal, it means that each, oh sorry, the pen is working fiddly today. Okay. Each space has length 1. We'd love to know what the pen is doing. Alright, so length 1. all of them, length 1, all of them, length 1. So that's what we want to create. How do we do that? So let's assume we have a curve. We want to generate frames. So think of these curves as 2D, right? So we are going to generate frames oriented along the curve. Something like this. So that's what we need to do. We need to generate 3 vectors. Position is easy, right? We actually, in our case, the positions are given to us. So that's less of a problem. Instead, if the function is defined mathematically, just evaluate the function, you get the position. So we have the position, this is check. We need 3 vectors. So the first vector is going to be tangent to the curve. We can easily do that by computing this vector between the 2 points, right? You know that computing the vector between the 2 points, let's say this is P2 and P1, it's really easy to do. It's just like P2 minus P1, right? P1. This is the vector, basically P1, P2, all right? That's how you compute it. So fine, we have the first vector. Now we need the second one. We need to know an up vector. The way parallel transfer works, and this is the key part you need to understand, is that you start with a given up vector, and then you update this up vector moving forward. Let me explain. So let's say that I give you a given up vector, this, straight up, so 0, 1, 0. This is our up vector, right? So we have this. That's all good. We have 2 vectors. We need to compute a third one, and this one needs to be perpendicular. So let's say this is the x vector and this is the y vector. We need to compute the z vector, and it needs to be perpendicular to both x and y. The way to do that is the cross product. The cross product will generate a perpendicular vector to both x and y, and the length of this vector will be proportional to the sine of the angle between the 2. But we are not worried about that because we're going to normalize it anyway. So we just do a cross product. So x cross y, right, is going to give us z. I'm not going into the detail of cross product. You can check it on Wikipedia or check Khan Academy for all that. Now we have this vector. You can think of it like coming straight out of the screen toward you. All right, so we have the 3 vectors, and we get something, as of now, in 3D, we will have something like this. It's a bit hard to draw, so this is perpendicular, z is perpendicular, but there is still the problem that y and x are not. So the way to do that is to do another cross product. So we are going to recompute, okay, the pen is weird, it's really weird. Is to recompute basically the y vector by doing a cross product with z and cross, so the x is the cross product x, so dot product with z and x, okay, which is gonna give us the new y, and that's it. So this is the old y we deleted, and we generate our orthonormal frame. Keep in mind that all this needs to be normalized. All those vectors, we're going to see that in the code. So you compute z, you normalize it. You compute x, you normalize it. You compute y, you normalize it. Now we want to compute the second frame, the one at P2, using P2 and P3. So as usual, we compute first the aim vector. Second, we need another up vector to do compute z. And we are going to use not the original up vector that was given to us, but we use the one we used for the previous iteration. So we are going to use this up vector, right? And we're going to compute this. And we keep moving forward. Oops, sorry, not like this. We keep moving forward like this. And that's how the computation works, right? And why is important to keep using the previous up vector? For 2 reasons. The first reason is that it's more stable. Let's see what happens if we do something like this. Okay, given up vector is this one. Let's put it. This is our given y, and we keep computing frame is fine. But what happens if we try to compute the frame here? this is our aim, and we do a cross product. Wow, super weird. The pen is wild today, I don't know why. Look at that. Anyway, we do a cross product between the y and the x. You will see that it's parallel. We are going to get a 0 vector because the sign of is going to be 0, all right, or 180. And that's the issue we're going to get. So the length of the vector is going to be 0, means we cannot normalize it and we cannot use it to compute again the other cross product. Instead, if you proceed in a relatively small step, all right, the up vector continues to update normally, and when you get here, you have a decent up vector where the gap is not too big, all right. So that's why it's really important. It keeps the operation more stable. Still, if you, even by updating the up vector, if you can take a gap too big and there is a big deformation like this in the curve, you're gonna get issues. Okay? But that's not so easy to get. And the second is that by keeping updating the up vector, you get some natural bank down the curve, right? So let's say that your curve is going down in a spiral. Your up vector starts to bank inward naturally, right? So it keeps a natural twisting along the curve rather than still being always straight up. And again, that might be an effect that you want or you don't. Okay? It's up to you. Might be good or not, but usually it's something that you want. But again, it's something also you might, if you don't, you might need to tolerate in order to get a stable up vector. And that's the theory behind it. That's how you compute your up vector, right? One extra thing I want to cover before we jump in the next video is that how we're going to represent that. We're going to represent that with a 4x4 matrix, which in Unity is a column major. All right, so again, I'm not going to deal with super in details. I kind of expect you to know a little bit about this, or you can go on Khan Academy. But the idea is that we are going to compute flow 3, which is our F vector, and we're going to lay them out in the columns of the matrix. So the first column is X, the second column is Y, the second column is Z. And the fourth column is going to be the position on the curve. All right. Then there is a bottom row, which is of padding in order to make the matrix square. And it's going to be padded with zeros except the value in the position column, which is going to be 1. Okay. That's how we're going to store. We're going to compute those matrices. It's just a way to compute this. You don't have to do it this way. You can even compute maybe a quaternion plus a position. And it's going to be more compact in memory. There are many ways to do it. I decided to do it with a matrix just because then it's easier to transform points around. But again, it's up to you how you want to do it. That's what we're going to do though. So in the next video, we are going and implement that in Unity. Alright guys, see you in the next video.